chapter 1, which is amplifier models or something like that, amplifiers. Right? So we're going to start talking about amplifiers in general, and then in the next chapter, chapter 2, we're going to start talking about operational amplifiers. Okay, operational amplifiers are a very special class of general amplifiers. So first, let's look at what are amplifiers in general. Okay, so amplifiers. So if I ask you the simplest definition of amplifiers, let's say my box is an amplifier. I have an input x of t. What should the output be for an amplifier?
Just a scalar.
Just a scalar, a times x of t. Right? So that will be, this is an amplifier. In the simplest way, that's the definition of my amplifier. Okay, and that's my amplification. Okay, so now that's where we're starting, but then we're going to start talking about how do you, if somebody gives you an amplifier, how do you analyze that? What sort of properties you want to look at, right? So, and how would you determine how much load it can drive, and all things like that, right? Okay, so let's see. So properties of interest. So the first one is obviously amplification, right? How much amplification are we getting from the amplifier? Second, input impedance, right? So if I look into the amplifier, how much is the input impedance? Right? Let's say if this is a box and there are two terminals coming out of it. If I look in, how much input resistance am I seeing looking in? This is Rn. Third, output impedance. R out. That means looking in here, that is R out. Okay. Again, if you're kind of a learner where writing down notes helps you follow, then obviously please do so. But if you're just writing down notes just to take notes, I'm going to scan this so you don't really have to do it. Okay. Okay, so we have input impedance, output impedance. Can you think of anything else which is of interest? Power gain, okay. So power gain sort of can be, how to say, inferred from these other properties, but that's something you want to look at. How much power can you add? How much power can the system add, right? Usually, there will be some certain limitations, right? So power gain is another thing. Okay, anything else? So I'll give you a hint. We discussed something about this at the beginning of the class.
Low pass filters and stuff like that.
So what about an amplifier you want to look at in that sense then?
Filter.
It's frequency response, right? It's frequency response. That if you have an amplifier, it's probably not going to amplify all frequency signals, right? It's going to amplify frequencies of certain range, and it's not going to amplify frequencies of. It may actually, reduce frequency signals in other frequencies, right? So if you have looked at, for example, if you bought a power supply like your speakers, usually if you look at its technical specifications, they will give you its bandwidth, right? And usually the bandwidth for your speakers would be around slightly greater than 20 hertz or 20 hertz to 18 to 20 kilohertz, right? And after that, it will flatten out. So if you buy a speaker, if you want to know how good that is, you want to look at its frequency response and see how flat the response is within that bandwidth, and how fast it drops off outside that bandwidth. That's a good call. That's a good indication of a good speaker. If you buy crappy speaker, it's going to be lots of ripply things, or it's going to look, the frequency response for a not so good speaker would look something like that. Okay, if you have a good speaker, it will look like that. Okay, so frequency response, not just for audio speakers, but any amplifier you build, is extremely important. Because if the frequency response is like that, within the range of frequencies you're interested, it will distort your signal. Right? So you just want an output like that, not some complex convolution of some impulse response. Right? So if the frequency response is not flat in the region you're interested in, then you're going to have to deal with it. Okay, so that's why frequency response is very important for an amplifier. So these are all the properties we'll be interested in for a given amplifier. Okay, all right. So now amplification is straightforward. Why we're interested in that? Because that's the primary purpose of our amplifier. Why do you think we're interested in input impedance? Any thoughts? That doesn't have to be the right, obviously.
It needs to have a certain amount of voltage or current running through it, so you need to have the input.
Okay. So let's say if an amplifier, if I have an amplifier, would I want it to have a high input impedance or a low input impedance? Why low input impedance? Okay, so I like how you're thinking. Okay, so this is again a good point of discussion. Let's say now we're talking about input impedance. I want you guys to, what do we want, right? What do we want? A, low, B, high. Discuss in your teams, and I will take a poll. Give you guys 2 minutes, and I want a reason, not just an answer. I want a reason why you think it should be low or high. Okay, go. For this purpose, please do not look at your textbook if you are doing so.
So we can or can't look at it?
Cannot. I want you guys to discuss based on what you already know. Okay, I'll give you a hint. So let's say we're talking about voltage amplifiers now, right? We're talking about voltage amplifiers, right? So actually the answer changes if you're talking about voltage amplifiers or current amplifiers. Okay, so let's talk about voltage amplifiers. You have a signal source, let's say VSIG, let's say this is a microphone, right? And it will have certain output impedance, RO. Okay, and then you're going to connect that to your amplifier, right? You're going to connect that here. And then if you look in here, that will be the input impedance, Rn. I'm asking you if should Rn be high or low. Okay, go.
The way he drew it, he's just talking about not the way there's still voltage source coming out, or voltage.
Yeah.
It's not.
At the output, you still have some voltage coming out. Yes.
So what we're talking about is maybe that's just something that just not the actual configuration of the
Okay. There seems to be one team with 4 members, all others are 2. So Moshe, I think you should join Ronaldo and Aaron here so that you guys even up. Okay, answers. High or low? How many say high? How many say low? Everybody. Okay. So your guys are saying low is the correct answer. Okay, why? So you're saying Rin should be low, right? Why?
Voltage or current?
This is a voltage source, right? And this is an amplifier, voltage amplifier.
We're talking about the one inside the amplifier.
Right, and this is the amplifier here. And we are talking about this Rn, whether this should be high or low. Okay, so when you say low, why should it be low?
We think we want to switch.
You want to switch. Okay. Okay, so you want to switch to high. So why do you think it should be high?
I'm pretty sure the current's supposed to be low.
Why?
I mean, when you look at like, if we're like, you know how Norton and Thevenin, when you have a current, you want that resistor to be, when a voltage source, you want a resistor to be low so you don't, or high so you gain the voltage.
So for a voltage source, you want resistance to be high. Is that what you're saying?
Yeah, for current you want the resistor to be high, and for voltage you want the resistor to be low.
Okay, so then you're talking about, so if this is a voltage source, my signal source, you want RO to be low or high?
low.
Low. Okay, so but I'm talking about Rn.
Yeah, we want that to be high.
Why? I agree with you that this should be low, ideally, right? Ideally this should be low, but I'm talking about this Rn, and you guys said that should be high. Why?
So you get the most voltage
Get the most voltage where?
in the actual amplifier.
In the amplifier. And how did you determine that?
Just the,
With the formula for the
You mean voltage divider rule?
Yeah.
Yeah, okay.
I was
So,
thinking voltage divider because we want Rn to be higher than Ro so we don't lose voltage.
right, okay, all right, good, thank you. So let me try to summarize. Jeremy and, can you remind me your name? Michael. Jeremy and Michael are saying. So what they're saying is the input to the amplifier is the voltage drop here, right? Because the voltage drop here is what the amplifier is seeing. It does not know what V sig is. So if you, let's say this is V in now, right? Then my V in will be equal to R in divided by RO plus Rn times V sig, right? Now, no matter what RO is, no matter what, whether that is low or high, the higher Rn is, the better, right? Because the higher Rn is, the more closer this will come to 1. And it can be max 1, right? So that means if my amplifier has a very high input impedance, no matter what signal source you connect to it, most of the voltage from the source will come across the amplifier. Okay, so we want a high input impedance. Got it?
So if we're calling Rn the input impedance, what is Ro?
Good question. Right? So that's the next point we are going to talk about. This is the output impedance of our amplifier. Right? So this is the output impedance of my signal source. Right? So let's say this here is a microphone. Let's see if I can draw a microphone. That is a microphone, not a mushroom. So this is a microphone, right? So usually, can microphones, let's say if you have a passive microphone, which is not like battery powered or anything, can it really give out any power? If you connect a passive microphone to a speaker, will you hear any sound?
It'll be extremely quiet.
Extremely quiet, and probably you don't hear anything,
Yeah.
right? It's because your microphone cannot put out any power. It's passive, right? That means if you try to draw current out of it, almost all the signal will be lost, right? So that means it has a very high output impedance RO. If you try to draw any current from it, your signal is gone inside the output impedance itself. But that's not how actually microphone works, but you can model it this way, right? So usually your signal sources, which are sensors, if they're passive sensors, they have very high output impedance because they cannot produce any output power. You cannot draw much current from it. Okay, so that is why you want your amplifiers to have very high input impedance so that you don't draw much current from it. That's another way of looking at it, right? If your input impedance is very high, you're not drawing any current from your microphone. That means you're not trying to get any power from your microphone. The power has to be supplied by the amplifier itself. That's why you have the amplifier, right? Okay. So the next thing we'll be talking about is output impedance. Right, so now we're going to try and complete the model for an amplifier. So let's say this is our amplifier. We already had our input impedance here, Rn. And let's say the voltage drop here at the input of the amplifier is Vn. Okay, and then we can model our amplifier. So the output should be some A times Vn, right? That's what we should expect at the output. Everybody with me? This could be a tricky question though. Trick question. Do you, right.
What's inside there? AVN?
This is a voltage source. Like it's a voltage dependent voltage source. I'm saying I should expect that to be the output. Do you agree?
Yes.
Okay. At the output of the amplifier. Okay. All right. Yes, that is correct. That's what I should expect. Okay. And then I have a output impedance RO for the amplifier itself. Okay. Now, let's talk about this. Should this RO be high or low?
Low.
Okay. Any other answers? Obviously, there are only two answers: low or high. Okay. Output impedance, low or high. Again, I'll give you guys a minute to discuss about it, and I want answers.
We're still talking about voltage.
Yes. Yeah, this is input voltage. That's a voltage dependent voltage source. Okay. Okay, answers. Low or high? How many say output impedance? How many say it should be low? How many say it should be high? Okay, all right, so answer is low is correct answer. Right? Okay, why? People who said low, let's see, Ryan, right? Ryan, why should it be low? Voltage at the output high. That's why you want the okay. All right. So what I think I'll try to express more mathematically what Ryan is trying to say. let's say for here, in this case, if you measure the output voltage here, what would you measure? If you don't connect anything, and you measure the output voltage, how much would you measure?
V out.
How much, in this case, how much would that be?
Should it be AV?
A times V in, right? So if you don't connect anything and measure the voltage, it will be A times V in. So that is why this A inside the model is called open circuit voltage gain. Right? So that will be the voltage gain you will see if you don't connect anything at the output. Right? And in general, you will denote that as AVO. V here means voltage gain, O means open circuit. So that's open.
Is that O subscript VO?
A and small subscript V, subscript O. Okay. Now let's say if I connect something here, which is a load. Obviously, if I have an amplifier, I want to ultimately end up connecting something to it, right? Right. And then my output voltage is really across my RO, RL, which is the load. Right. And if I measure again, if I use the voltage divider rule, so that will be VO would be RL divided by RO plus RL times Vin. Times AVO times Vn. That would be my voltage across the load resistance. Again, no matter what RL is, if RO is very small, then this fraction will be close to 1, and it can be max 1. Right? Ideally, RO should be 0, so that I'll get the entire voltage gain across my load resistance. Right? Now, smaller RL is, the smaller RO should be. Okay, if RO is not 0, the smaller RL is, the smaller RO should be. So it means RL is small, that means it's a very high load, right? If you have a high power device, that means its resistance will be very small because it will try to draw a lot of power, a lot of current from it. So if you have a very high load, that means you will need an amplifier which has a very low output impedance. So usually you'll have many different classes of amplifiers. Some are called power amplifiers. Power amplifiers will have much less voltage output resistance than regular voltage amplifiers. So usually when you design let's say speakers, there you'll have something called a preamp, which will just amplify the voltage, and then there will be actually have the power amplifier, which will amplify the power. You'll try to do it in 2 stages, because usually you cannot have both at the same time, and we'll see that when we're designing amplifiers. Okay, so the bottom line is, the smaller RL is, the smaller RO should be. Ideally, RO should be 0 so that you don't care about RL, but in general that's not possible. Okay, any questions here? All right. So the other 2 are pretty straightforward. Here is we have power gain. How would you measure power gain? Output power divided by the input power. How much power is going in from how much power are you drawing from your signal source? That's your input power. Output power is how much power are you delivering to your load. Okay. Now you can also measure something else called power efficiency. Again, all these definitions are in your textbook. I would recommend you guys read it. Power efficiency means now you're talking about how much power are you delivering to your load divided by how much power are you taking in from the power supplies. Okay, so all amplifiers are active power supplies, right? So they have their own, most of the time you'll have DC power supplies. So they have their own DC power supplies. You're applying is input signal, and at the output you'll have a amplified signal, probably with higher power at the output too. Right? So your signal source, let's say microphone, is not really supplying any power. Right? All the power you are getting at the output is coming from the batteries. And those are usually DC power.
From the what, the batteries?
From the batteries,
Okay.
or your power supplies. And those are usually DC power. So an amplifier is really converting DC power into AC power. Right? And the way it is converting that according to how your input is changing, input signal is changing. Right? So it's, in a way, your amplifiers are DC to AC converters. Right? But you need an AC signal already, so you don't really call it converters. but it will convert the DC power into AC power. Okay. All right, and so that's power gain, power efficiency. How would you define frequency responses? Again, straightforward. Ideally, you want a completely flat line to infinity. Again, you don't have an infinite bandwidth amplifiers in reality, so you would probably have an amplifier which has a finite bandwidth. Okay. So now let's talk about how to measure these things. Let's say I want to measure input impedance, Rn. How would I do it? Right. So I have an amplifier. I don't care what's inside. I'm going to model it from the input side as if it has a resistance Rn, and I want to measure what that Rn is. And usually, if it's a good amplifier, I know it's going to be pretty high. How am I going to measure it? I'm just going to take a digital multimeter, connect it. Is there another way?
Look at the specs.
Look at the specs. Okay. If I want you to construct a small circuit and figure that out. Usually, the problem with digital multimeters is when you have very high input impedances, then they're not very accurate. Because multimeters have their own input impedances, which are around megaohms. Amplifiers also have input impedance around megaohms, so they will not be very accurate. So if I want you to construct a small circuit and figure that out, how would you do it?
Kind of like hard Thevenin.
What do you mean hard Thevenin?
Like you mean like actually calculate it by hand?
Right. Let's say I give you a box. I say that's in my amplifier. Don't use a digital multimeter to measure the input impedance. Like you have other resistors and everything in your lab. Make a small circuit, and I'm asking you to figure out the input resistance. How would you do it? Mm-hmm. Okay, so put a voltage source, let's say some VSEC, and then connect to it. Is that what you're saying? Okay, how would you figure out what Rn is from that? Moshe, you had something?
Well, maybe add another resistor in there to
Here, like this?
Yeah, measure across.
Let's say R. And if you pick a very high resistance, let's say around 1 mega ohm, then you just measure the voltage here. Use the voltage divider formula to figure out Rn. Right? Now you can measure, if this is VSEC, we can measure Vin using a multimeter, right? And then Vin will be equal to R divided by R plus Rn times VSEC. And you measure your R like that. Okay, so now I say I want to measure the output impedance, RO. How would I measure the output impedance?
If RO is low, use multimeter.
So again, let's say using multimeter is not an option again here, because these terminals are not passive anymore, they're active terminals, right? So it's like connecting a multimeter to a battery, to a power supply. You won't get the resistance from it.
Can you remove the office hours?
I mean, don't get rid of your office hours. You can just set up your
Sorry, okay.
So,
How would I figure out what RO is?
Same process. Could you hook up another resistor?
Put another resistor there,
Yep.
RL, and measure the output voltage there. Okay, but if you want to do that, you don't know what the gain is first, right? So you know what Vin is, you don't know what A is, because I just gave you an amplifier and said that's some box. You don't know what the gain is. So before you do that, you don't connect anything. Measure the voltage, figure out what AVO is. Once you figure out what AVO is, then you can use that formula to figure out what the RO is. Okay.
So when we were finding what input impedance was, you're saying measure across those two leads with a multimeter and then do your calculations? See?
The input resistance? Yeah, measure across this point and this point what the input voltage is.
Okay.
Right? So you know what this is because you just set it on a function generator.
Okay. So, yeah, I didn't know you were using a multimeter in that case. I thought you just used that formula.
Right. So measuring voltage is still accurate with multimeters, right? But if you have very high input impedance, then you cannot accurately measure the input impedance using a multimeter. So you can measure voltage accurately, so you measure that. Okay.
And then you just solve for R.
But
That makes
So for this formula where you get the measurement for V in, are we not using R in the numerator since we're measuring
oh,
the input?
thank you. Should be RN. All right. So Moshe, is that the right way to pronounce it?
Yes.
Okay. 0.25. Right.
Is this overall grade or just on the test?
No, it's overall. That I know that's
Please give a lot more of those.
that's a huge deal, right? So, I mean, total amount of extra credits I'm giving is 5 points, right, including catch-my mistakes and other extra credit problems. And if you get those extra credit, that means you bump up 1 grade level, right? In fact, let's say if you're at the border, you don't need all those 5 points either. Even if you get 2 points, you may bump up 1 grade level, right? So.
Did you write down me and my time?
Oh no, those were not extra credit problems. Only the first problem was extra credit problem. I will announce it if it's an extra credit problem.
Yeah, you were here for it.
Okay, so in the lab this week, I'm gonna give you a black box.
You can't give us a scenario.
Okay, I'm gonna say this is an amplifier, and I'm gonna ask you to measure all this stuff.
All right, so
And you already know how to measure frequency response, so we're gonna measure that too. Sorry.
So I remember you said for the R on the input impedance was supposed to be very high, but for the R on the outside, that one's supposed to be very low.
That's right.
Okay.
So you're probably gonna want to use a low resistance there.
So why is it RO? Are those the same? Do you want it to be the same?
Yeah, and this should probably be, let's say, RL to notation later.
Okay.
Yeah, but yeah.
The RL in this case needs to be low. Got it.
Okay. Yeah, you don't know what arrow is, so you cannot select arrow. Good. All right. Stop there.
What have we got?